Assalamualaikum warahmatullahi wabarakatuh to my respected panels. My name is Aidil Haikal bin Matsahir, student ID 2019416158. My final year project's title is Oil Palm Front Fiber and Zinc Oxide Reinforced Recycled Polypropylene Composite. My supervisor is Dr. Fridawati binti Rashidi Wong. I would like to thank Dr. Frida for her guidance and support towards me to fulfill the requirements for my final year project. For the presentation outlines, it consists of the introduction, literature review, problem statement and objective, scope and limitations, methodology, and lastly is expected results. The introduction for my final year project. Biopolymers that come from either plants or animals are known as natural fibers. Natural fibers made from plants primarily contain cellulose, whereas natural fiber made from animals primarily contain proteins. Natural fibers derived from plants vary greatly in their characteristics. The application of natural fiber as referencing is currently the best method for creating eco-friendly composite. Global population have begun to embrace the use of natural fiber and biopolymers in numerous items in recent years due to the drastic drop in petroleum supplies and worries about the consumption of synthetic plastic. Thus, in this study, a composite comprised of recycled polypropylene and oil palm front fiber reinforced with zinc oxide is created as the alternative way to reduce this loss due to the availability of oil palm fiber as the substantial amount of waste produced. Oil palm contains lignocellulosic biomass, which includes the oil palm trunk, empathy fruit punch, and fronds of all of which have the potential to become biomaterials. However, they are not being used sufficiently right now. Therefore, maximizing the use that may be made of waste has advantageous economic and environmental outcomes. Numerous types of research have been conducted on different lignocellulosic biomass pre-treatment method, but none was done to review this method in relation to the effectiveness in converting to value-added chemicals. This paper reviews the available and potential pre-treatment methods for oil palm biomass and assesses the effectiveness of each pre-treatment method based on factors affecting the conversion to value-added chemical. The successful conversion of lignocellulosic biomass needs an effective pre-treatment as an important step to optimize the process. Next, the literature review for natural fiber. Dispersed phases of synthetic fibers include glass, carbon, bauxite, and Kevlar in composite structures have been found in improved material qualities, including high strength, stiffness, and resistance to chemicals, temperature, and wear. There are drawbacks to natural fiber as well, including higher hydrophilicity that encourage microbial attack, fiber degradation, and poor compatibility with a hydrophobic polymer matrix. Interfacial bond strength is typically low and requires surface treatment, which causes fiber to pull away from the matrix. In study by Gideon and Atali 2022, it has been evidenced that the jute fiber, which has low tensile strength and elongation, may break first, and that the load is then carried by the palm leaf fiber, which has high strength and elongation, without the failure of the matrix. This better stress transfer from matrix to fibers leads to an increase in the mechanical properties of the hybrid composite. Another factor is that palm leaf fibers' high cellulose content also helps to improve the mechanical qualities of the composite. Additionally, the decrease in tensile strength is brought on by an unfavorable level of compatibility between the matrix and lignin in the interfacial region. Lignin decreases the bending mechanical characteristic of the composite material. These natural fibers can be chemically treated with water repellent, coupling agent, surface alteration, chemical or physical, and heat treatment to get beyond this restriction. This alteration can aid in changing the properties of the resulting biopolymer composites, enabling them to compete with the traditional polymer components. Natural fibers that have been chemically treated exhibit increased impact toughness and fatigue strength. For the chemical treatment is widely used in manufacturing composite because of its effectiveness. The alkaline treatment not only eliminates the sugar from the OPF surface but also any natural impurities, resulting in larger pores. As a result, the surface becomes more porous and rougher. which enhance the mechanical interlocking with the matrix to strengthen the interfacial adhesion between the fibers and the polymer matrix. Sodium hydroxide NOH is briefly added to the fiber at a concentration of 5 until 6%. Another study was conducted utilizing dilute nitric acid HNO3 as a chemical treatment for the hemispheres found in oil palm fronds. Thus, alkali treatment by using sodium hydroxide was chosen for this study as among the chemical treatment, alkalinization is one of the most economical and commonly used chemical treatment for natural fiber. For the flexural strength in research for Ashraf et al. 2022, the results show that 50% of PF loading provided the highest flexural strength of 1.4306 MPa. However, they anticipated that after using a high fiber load in the composite system, the mechanical performance will decrease. As revealed by the morphological study in the experiment, fiber pull-up was the cause of this decrease. It happened because the composite strength was reduced by insufficient wetting between the fibers and matrix. The tensile and flexural performance of the composite was also improved by the coupling agent. The increased interfacial connection between the fiber and the matrix was credited for the improvement in mechanical properties following the addition of MAPP. Additionally, the study confirmed that the flexural test result for the treated OPF fiber composite show superior strength and modulus in comparison to the untreated OPF fiber due to the close connection between the matrix and the fiber. The flexural and impact strength of sisal or palm fiber reinforced hybrid composites increase as palm fiber content increases. For the tensile strength, a composite material with high tensile strength gains great fibrous strength, outstanding durability, and better adhesion between the matrix and the pressure phase. Due to insufficient fiber matrix adhesion, a composite tensile strength may be decreased. Hassana and Ali 2022 published the effect of reinforcing epoxide composite with a filler derived from a chopped agricultural waste from oil palm. According to the finding of this study, the tensile strength of the epoxy plus oil palm composite decreased as the weight percentage of oil palm rose but increased to 29.224 MPa for epoxy plus oil palm plus 5% zinc oxide samples. As the weight percentage of OP and zinc oxide increase, the Young modulus increase, and the elongation decreases from 9.6 to 6.8%. The treated fibers provided a better cross-linking mechanism between the matrix and the reinforced fiber vehicles due to ineffective stress transmission from the epoxy matrix under loading condition brought on by a hydrophilic factor of 4 adhesive capacity between the oil palm fiber and epoxy matrix. The influence of varying OP filler loads on the strength properties of epoxy composites decreased. Next, the impact strength. The impact strength rose, indicating that the type and volume of the fiber are more likely to be connected to the degree of internal damage during impact loading. This composite fiber exhibited higher mechanical strength and less internal damage under stress test. The homogeneous epoxy specimen because it had the highest concentration of cellulose in its chemical composition. In comparison to composite without zinc oxide, the impact strength of the composite material reinforced with EFB and zinc oxide rose considerably. In comparison to EFB fiber mesh size 40, 60, and 80, specimens with a 50% zinc oxide composition and a 100 mesh EFB fiber had the highest impact value. Hardness test. Adding zinc oxide to epoxy and oil palm composites resulted in the increase of the hardness values by increasing zinc oxide and improved when using particle zinc oxide as reinforced epoxy or oil palm. The reason for such significant behavior might be related to increased strength in particulate composite materials by increasing fracture surface area which arise from an uneven crack growth caused by particles serving as an obstruction in front of crack propagation, and the requirement for more energy for crack growth. Thermogravimetric analysis (TGA). The thermal behavior of natural fiber composites depend on the principal constituent, natural fiber and matrix type of the composite. Natural fibers derivative thermogravimetric test (TG) curve demonstrates the removal of water and thermal degradation of the fiber cellulose constituents. Peaks in each degradation region on the DTG curve represent the fiber constituents and demonstrate the greatest rate of peak thermal decomposition. Thermal stability is improved with the increase in organic filler content. Composite with a smaller concentration of fiber degrade more quickly and only experience one degradation peak. Next, the problem statement and the objective. The oil palm fiber reinforcing polymer mechanical qualities, modulus, hardness, and toughness are insufficient for many end-use applications. The main reason for this restriction include delamination, insufficient impact resistance, inherent breakage, and fracture hardness behavior. Furthermore, a notable disadvantage of lignocellulosic fiber as reinforcement is their polarity, which make them incompatible with a hydrophobic thermoplastic matrix. This incompatibility results in poor interfacial bonding between the fiber and the matrix. This in turn leads to impaired mechanical properties of the composite. The utilization of untreated natural fiber may be hampered by quality variation, high moisture absorption, and low processing temperature. There are two main objectives for this study. First is to optimize the composition of the composite in order to achieve higher mechanical properties. And the second objective is to improve the chemical characteristic of the composite by using a suitable chemical treatment. Next, for the scope and limitation. This project scope is to analyze the mechanical and chemical properties with a focus on producing oil palm from fiber and zinc oxide reinforced recycled polypropylene. The varying composition of the oil palm from fiber and polypropylene was set up, which are 50, 30, 45, 60, and 70% for oil palm from fiber, and 80, 65, 50, 35, and 20% for PP. The composition of zinc oxide, which is 5%, was fixed. 5 number of samples were fabricated and tested for each composition of the composite. The oil palm from fiber will be treated with alkaline treatment before the composite is produced by an extrusion compression molding process. All 25 samples were observed in the mechanical and chemical tests, including fracture, tensile, impact, hardness, and thermogravimetric analysis tests. All tests are done in accordance to the STM standard for each test. Next, the methodology. In this experiment, three main materials are used, which are recycled polypropylene plus oil palm from fiber plus zinc oxide powder. For 3.1 fiber extraction, oil palm from fiber was cut into short components. The fiber was crushed using the sieving process can be done to get 60 mesh by using a sieving machine. And the alkaline treatment, the fiber was immersed in 5% NaOH solution for 4 hours at room temperature, 21 until 28 degrees Celsius. The fiber will then rinse multiple times with distilled water before being immersed in very diluted HCl to remove the NaOH that had adhered to the surface. Finally, the fiber will rinse multiple times with distilled water before being dried in a 60 degrees Celsius oven for 2 hours. For sample preparation, the method used an extrusion compression molding process (ECM), and the mechanical properties test includes fractural, tensile, impact, hardness, and thermogravimetric analysis (TGA test). Lastly, expected result. 4.1 fractural strength. Based on findings from earlier studies, it was determined that the mechanical performance of a composite system will degrade after utilizing a high fiber load. The morphology analysis conducted during this experiment indicate the fiber pull-out was the root cause of this decline. It took place as a result of inadequate wetting between the fibers and matrix, which decreased the strength of the composite. 4.2 Tensile strength. High tensile strength composite material provide excellent durability, great fiber strength, and stronger adhesion between the matrix and dispersion phase. The tensile strength of a composite may be reduced as a result of poor fiber matrix adhesion. With zinc oxide, the Young modulus increases as elongation decreases. On the other hand, the decrease in tensile strength is caused by an unfavorable level of compatibility between the lignin and the matrix at the integration area. 4.3 Impact strength. This composite fiber exhibited higher mechanical strength and less internal damage under stress than the homogeneous epoxy specimen because it had the highest concentration of cellulose in its chemical composition. The impact strength of the composite material reinforced with EFB and zinc oxide increases significantly when compared to composite without zinc oxide. 4.4 Hardness. The hardness value increased when zinc oxide was added to epoxy and oil palm composite, and they improved when zinc oxide particles were used to strengthen the epoxy and oil palm. For the 4.5 thermogravimetric analysis (TGA), as the amount of organic failure increases, thermal stability gets better. The failure's inability to be dispersed uniformly throughout the matrix may be the cause of the anticipated decline in RHDPA and oil palm fiber 50. Composites with a low fiber content deteriorate more quickly and only experience one fade. I would like to thank the respected panels and have a nice day.